Welcome to today's Explainer. We're diving straight into the heart of offshore power. We're going to look at that perfect, chaotic collision between the heavy-duty reality of industrial engineering and the super-precise world of thermodynamics. It's going to be a really fun ride.
Here's our roadmap for today. We'll hit the offshore powerhouse, unpack the Joule Brayton cycle, calculate turbine work, look at the massive compressor energy tax, and wrap up with real-world inefficiencies. Let's get right into it.
Section 1. The Offshore Powerhouse.
Okay, picture this. If you've ever stood on the deck of an FPSO in the Gulf of Mexico at, say, 2 a.m., you know exactly what this feels like. You've got 35 degrees Celsius heat, practically 100% humidity, and there is this constant, heavy vibration rattling right through the steel deck into your boots.
Well, that vibration, that's a gas turbine generator just screaming at 3,000 RPM. It's burning wellhead gas to push out literally every single watt of electricity on board. It's the absolute heartbeat of your entire offshore power system. Because, if this thing trips, boom, everything goes dark.
Moving to Section 2, the Joule Brayton cycle.
So how does this beast actually work? It all comes down to the Joule Brayton cycle, which is basically the fundamental thermodynamic blueprint for these heat engines. As we map this out on a pressure-volume diagram, you can literally trace the cycle across 4 distinct points. We move from intake right here at point 1 up to compression at 2, across to combustion at point 3, and down to expansion at point 4. The engine just continuously draws out this loop.
Basically, the machine is operating in 3 continuous stages to make this happen. First up, we compress, drawing in massive amounts of ambient air and squeezing it tight. Then, we combust, mixing in fuel and igniting it into a continuous, roaring flame. And finally, expand, letting that violently hot gas blast through to drive the power turbine. So just remember, compress, combust, expand.
Section 3. Calculating turbine work. Now let's look at the math, starting with the work done by the compressor itself. It takes a massive amount of energy to squeeze all that air. In this formula, notice the Greek letter gamma, which represents the ratio of specific heats. We're tracking that right alongside the huge shifts in pressure and volume from our initial state to that highly pressurized state right before combustion.
After that, we calculate the actual turbine work, and it's a beautifully elegant formula. You just take the specific heat of the gas and multiply it by the massive temperature drop from the red-hot turbine inlet, that's T3, down to the cooler exhaust at T4. That temperature delta, that drop, is literally your mechanical work output.
Section 4. The compressor energy tax.
But here is the wild part, kind of a plot twist in our engineering story. A staggering 50 to 60% of your gross turbine output goes right back into driving the compressor. Just look at how this energy flow splits off. The system is practically cannibalizing itself just to keep breathing. That leaves us with only the remainder, around 45% or so, as net shaft output for actual power generation. Crazy, right?
Section 5. Real-world inefficiencies.
And hey, that 45% is just on paper. In the real world, even a shiny, perfectly clean engine is going to suffer. It's kind of a death by 1,000 cuts. Got dirty blades and aging conditions? That's about a 5% derating loss right there. Mechanical friction from the speed-reducing gearbox. There goes another 1.5 to 2%. Then your generator's electromechanical conversion process eats another 2 to 4%. Add in your continuous auxiliary loads, things like lube oil pumps and cooling fans, and you are losing another 1 to 5%.
So, when you actually multiply all these practical derating factors together, the turbine thermal efficiency, the gearbox, the generator, your overall thermal efficiency for usable power drops down to roughly 30%. 30%! Think about that. All that fire, all that extreme pressure, just to actually capture less than 1/3 of the potential energy.
Which brings me to a final thought for you to chew on. If our heavy-duty engines are taxing themselves this heavily just to operate, what radical design changes are waiting out there to break this cycle? Can we completely rethink how we compress, combust, and expand? Thanks so much for joining me on today's Explainer. Keep questioning the mechanics behind everything around you, and I will see you next time.